So now I'd like to introduce you to the basics of modern classical mechanics. And our goal today is to introduce you to a model that should be more intuitive, provide equations that yield better mathematical results, and provides a mechanism for explaining things about other models like relativity that those other models would have difficulty explaining. Ideas like what is time dilation, length contraction, and the twin paradox, and why does relativity absolutely require them, is something we can now answer. And at the same time, we'll be able to answer why a model like modern classical mechanics doesn't require it. Now, before I move on, I just want to say one thing about modern classical mechanics. And in prior episodes and podcasts, you may have heard me talk about the model of complete and incomplete coordinate systems. So just think of modern classical mechanics as version 2 of that earlier model. The main idea behind classical mechanics is to make it intuitive. We're going to build on things that you're probably already familiar with. And the main concept is one of a system. Now, there are a couple of rules that we have in modern classical mechanics. One is a system is 1, 2, or 3 dimensions. So far, we haven't found a need for more. Systems can be placed entirely on or in other systems. Systems move with respect to respect to the system on or in which they were placed, and depending on how you view the system, you can think of it in terms of being a particle or a wave. But the key concept is one of a system. And as we already mentioned, a system can be one-dimensional, which is a line, two-dimensional, which is a plane, or three-dimensional, which is a space. So let's stay with the two-dimensional system for a moment and just plot our first system. Since it's our first system, there isn't another system in existence yet. We call this our outer coordinate system. Now, our second rule said, or one of our rules said that systems can only move with respect to other systems. So since there's not another system, this is somewhat rather uninteresting. So in order to make things more interesting, we have to plot a second system. This one we will call an inner coordinate system. And this, of course, is interesting because it can move. And it can move in one of a number of different ways. One way we can say is that it slides. You can slide it left, right, up, down. All of these slide type motions we call translation. We can also stretch it in much the same way you would stretch a rubber band or a slinky. We call this scaling. Third, you can turn it and point it in all sorts of different directions. We call this rotation. And fourth, you can flip it almost the same way that an image is flipped when looking in a mirror, and we call this reflection. Now, all 4 of these types of transformations are basic geometric transformations that are well understood and well explained both theoretically, conceptually, and mathematically in many textbooks. So we're not going to go into the math here. However, we can say that in mathematics, you can find the topic discussed in geometric transformations, and in computer science, you'll find it often discussed in textbooks or in courses on computer graphics. Now, by itself, this isn't enough to explain all the observations that we see in many of the experiments that have been performed in areas like special relativity. So for that, we actually have to add a third system. So this black box we will add, and this is going to be our third system. In order to avoid name confusion, we're going to call this moving phenomena. So when we add this moving phenomena to the outer system, we have two inner systems, an inner system, a moving phenomena, and both of those are plotted on the outer system. This is an incomplete system relationship. Then, if we were to plot that moving phenomena on the inner system, which itself is plotted on the outer system, this nested relationship is a complete system relationship. Both of these are important because they help us distinguish how that moving phenomena is going to behave when the inner system is moving. So as you can see, we will have 2 sets of equations. One that explains what's occurring with the inner system, and one that explains what's going on with the moving phenomena. And that's a very important distinction between this model and relativity theory. So here we see both systems. Now what's interesting is when we put everything in motion. So what we will do with the inner system is we will just put it into translation motion. We will just slide it across the outer system. And while that's occurring, we will ask the moving phenomena to just oscillate between points P and Q. So you can see in one case, it's going to oscillate with respect to points P and Q with respect to the inner system. So its motion is governed by the inner system. That's a complete system relationship. And as the moving phenomena is oscillating between points in Q, P and Q, but it's moving with respect to the outer system, that's an incomplete system relationship. And we'll show some illustrations of this next. First, let's view that moving phenomena and show its behavior if it's a particle. On the left-hand side, we have a complete system relationship, and it behaves just from the perspective of the moving phenomena. There's no difference when the inner system is moving or when it's stationary. So there is an equation that tells us what's occurred to the inner system, but from a moving phenomena perspective, its oscillating behavior, it has not changed. When we look at the incomplete system relationship on the right-hand side, we can see that because we're asking the moving phenomena to oscillate between the front and back of the inner system, but its motion is governed by the outer system, we get this long line, short line oscillation behavior. So that's something that's really important for us to recognize. Now, another thing that's a very important point is that when we talk about particles and we look at long lines and short lines and figure out how they behave, the main thing that we're looking at is their additive behavior. So the main operation here is addition. And when we look at waves, they behave slightly differently because we look at wavelength as opposed to length. And I'm illustrating a wave just as one wave as a circle. So if we look beginning with an incomplete system relationship, a circle may start at one point. Imagine yourself as being in a rowboat with a friend and the boat is moving down the stream and you splash your hand in the water. Well, the boat's going in a certain direction. Eventually the wave will hit your friend. When the wave hits your friend, you splash your hand, hit his hand, and then the wave propagates back towards you. But since the boat is now moving towards the wave, it actually reaches you quicker than when you were stationary, or than the amount of time it took for your wave to reach your friend. And again, we create this long line, short line relationship. Now, just graphically, if we're looking at a long line, short line, we might not notice something. But because this is wavelength, we talk about wavelength in completely different terms than length. And when we do this, we look at concepts like the superposition of waves principles. We can also look at it from a frequency perspective. And what this means is that mathematically, when we look at things, we look at it using averages, not addition. Now, when we look at a complete system relationship, you can see that there's no difference, as the case when the boat in this case was stationary. So it's very, very similar to what we saw with the particle mathematically. Now, there is an error on this drawing because the wave technically would not propagate outside of the inner system. The lines that you see drawn in the outer system really don't exist. So the drawing should look like this, although if I presented this picture first, it would be hard to understand what was going on. So there are a couple of examples which you can read on this particular slide. I won't go on this in detail. Today I used a boat example, and so if you think of a boat that has water on the outside or water on the inside, that will help you understand how waves are behaving in modern classical mechanics. And if you are using the bus example, which I've given many, many times before, that gives you an understanding of how particles would behave, where particles will be described with length and waves will be described using wavelength.